Okay, so let's start. So in the last few classes, we have been looking at the single stage OTA, and I mean, to give a quick recollection, we started with this common source amplifier. Then we told we have to amplify the difference between two signals, and so that resulted in this differential pair. And then we told that to increase the gain, instead of having this resistor here, we'll replace it by an active device with this current source. So we added a PMOS transistor here, and then finally we saw that this is connected, and finally we saw to generate this bias voltage, we can have a current mirror, PMOS current mirror, and that basically gave rise to the final structure we have. Right, and we also, looked at the small signal gain of this, and being an asymmetrical circuit, we calculated the gain using the short circuit GM times the output resistance. Of course, in your assignment, I will ask you to derive why this makes sense, and you'll know what are the assumptions behind this, or is it valid all the time. Okay. And if I label these transistors this way, what is the short circuit GM here? GM was GM1, and what was R out? It was the parallel combination of the NMOS and the PMOS R outs. Great. And in the last class, we also looked at the common mode range, both at the input and at the output. So basically, you'll have at the input, you'll have a minimum DC you can apply, and a maximum common mode. Similarly, you will have something at the output also. Okay. So now, if this OTA were to be used or to be connected in some kind of a feedback, say put it in unity feedback like this, I know that if Vi is here, what will be this node voltage ideally? That will also be Vi, so which means this guy is also Vi, right? So although independently the input and output have a range of voltages that can be tolerated, when you put it in a feedback like this, so what will be the final, what I'm saying is, if I don't make this connection, at the input I'll have some minimum voltage that I can apply, output there is some minimum I can apply. Now I'm enforcing Vi to be equal to V out. So what is the absolute minimum I can apply? There are two minimums. Which one I'll choose? Lesser? Okay, simple, right? What I'm saying is, this is the range from 0 to VDD. Let's say one guy is fixing it from here to here. Say the other guy is fixing from here to here. What will you choose? No, that's a maximum of the minimum, right? This is the minimum one. This is the minimum 2. We'll be limited by this guy finally, and in the upper end we'll be limited by this guy. Fine. So the absolute minimum will be the maximum of the two minimums, and similarly the maximum you can apply will be the minimum of these maximum voltages. Fine. Great. And let me see, I have copied it already. So in the last class, we also looked at the idea of slew rate, right? So again, the issue was when we have it in a feedback like this, and say we drive a capacitive load CL, if I apply an input step delta V times U of t, we know that the maximum slope for the output occurs at what time instant? T equal to 0 plus. And at t equal to 0 plus, it's as if the feedback is not yet active because the capacitor is still uncharged. So I can break the feedback. So it's as though I applied a differential step directly to the OTA, and we'll have the capacitor, and we saw that for delta V greater than a particular delta V max, this tail current I naught gets completely steered to one of the branches, and say this guy gets completely cut off. So the current I naught flows like this. So here these two guys are current mirrors, so the same current will be mirrored in this branch and flow through the capacitor. So what was the slew rate? It was I naught by CL. Okay, linear current I naught constant current I naught charging a capacitor, so the slope is I naught by CL. Great. And what was this delta V max? Does anyone remember? Yeah, root 2 times the gate to source voltage, the overdrive voltage. So I'll just write it as VOV in short of the transistor 1, M1, M2 at a current of I naught by 2. Great. So one last thing. So, oopsie. So here, let's say I try to sketch the difference in the two currents as a function of the delta V I apply at the input. Okay. So when delta V is 0, what can you say about the difference in the currents? 0, because both of them will be carrying I naught by 2 and I naught by 2. If I increase delta V, what happens to the differential current? It will increase linearly. What is the slope? No, I'm asking not the slope of the output voltage, slope of this graph. I mean, everyone is fine that it's going to be GM, right? If I apply a delta V difference, the current will be GM delta V, right? See, and again, this I1 minus I2 is basically, if you short this guy, what will be the current flowing here? So this current is I1, that will get mirrored here. I2 is flowing down, so what is the current flowing through the short circuit? That's basically this, right? We already saw how to calculate short circuit GMs and stuff. That's basically the same thing. So for small delta V's, it's going to go as GM times delta V, and beyond this delta V max, what will happen to I1 minus I2? It will be I naught, right? Because current is completely going to one branch. So let's say this is I naught, it will look something like this. Okay, this will be minus I naught. Right. Again, this is not completely linear. For small ranges, it will be linear, and then it will slowly do something. Okay. Great. So now this 5 transistor OTA is actually pretty good. It will offer a decent gain, but in practice we need much higher gains. Okay, for to give a range, probably this can get you gains probably at max 100 or something, but you might need gains of the order of millions or so. Okay, so this is not good enough. So let's see what all we can do to increase this gain. And here we know that the gain was basically some GM times R out, right? So if I had to increase this gain, one option is to increase GM or to increase R out. So GM was basically the transconductance of some MOSFET. So beyond some limit, it becomes difficult for you to increase it, right? So let's see what we can do to increase the output resistance. Okay, and for that, let's start from here. So what I'll do is I'll take this 1/2. We'll see how to increase the output resistance of this, and we know directly how to go from the first to the last guy. Okay. So let me look at this guy. I'm trying to find the output resistance here. So say call this M2 and M8. What is the output? I mean, for output resistance, I'll short everything else. So what is the output resistance? Yeah, it's a parallel R02. That fine? I mean, gates and sources are all incrementally short, so there is no GMVGS, only the R0s. Okay, great. So if you think about it, if I take only the PMOS guy, okay. So we know this is R08. Okay, incrementally the gate is short, but I mean ideally we'll connect it to some DC, right? So this PMOS transistor basically acts like a current source, right? Because I am biasing it with a constant source to gate voltage and it's pushing a current. It's acting like a current source basically. That fine? And if this were an ideal current source, what would be its output resistance? Infinite, and we are all set, right? There is no need to teach further. Course is done, but unfortunately it is not the case. So we'll see what to do. Now we know this is not a great current source, but do you guys know a technique to make it a better current source? We know how we can put a current buffer, right? So this is not a great current source, but we can put a current buffer, which is basically a common gate configuration. Fine. Again, I am drawing only the incremental equivalent. So this is the main current source. And what configuration is this now? What is this called? We already saw with NMOS case, right? If we have this, what was this called? It's a cascode. Okay, this is basically the PMOS cascode. That's all. It's no difference here. And this is basically the cascode device. Okay. Great. So now if I call this guy M8 and this M6. Now what is the output resistance? Is the output resistance of the cascode? What is this? Yeah, here I've labeled the transistors, right? R08
plus R06 plus GM6.
Yeah, GM6 R06 R08. Okay. So what is this approximately equal to? I mean, what? Only the last term is going to dominate, right? I mean, it's not complicate things. This is GM6. Fine. Push it up. Oops. Great. So now we know how to make a better current source. Now we can try to use it at the load side. So again, let me push it up, make some space. So this is the NMOS, and say I try to do this, put a cascode like this. Okay. So this is M2, let's say M6 and M8. Now what is the output resistance? Now what is the output resistance here? Yeah, so here it's basically, I mean, basically if I just put a cascode on one side, the output resistance is R02 parallel whatever you calculated, this big guy. So what is this finally dominated by?
This big.
No, you have a large, by the small resistance R02, right? So this is not buying you anything. So what should you do? I mean, if I had PMOS cascode, I see output resistance increases a lot. But if I just put it here directly, it's not helping because finally it's getting dominated by this guy.
We put buffer down.
Yeah, same thing. We'll put a cascode for the NMOS also. That's all. So that gives rise to this guy. That's all. Okay. So this is say M2, M4, M6 and M8, and this is where I'll apply the input delta V. this is out. So now what is the gain here? If the gate is at delta V, what is V out? Huh? So if I apply delta V, the current is GM2 times delta V. That times the output resistance is GM2 times delta V is the current times the output resistance we have. And what is the output resistance here? So basically we have a cascode, NMOS cascode looking down and a PMOS cascode looking up. It will be the parallel resistance of these two cascodes. So what is the NMOS cascode, impedance of the NMOS cascode? Roughly it's GM4 R04 times R02. So this in parallel with GM6 R06 times R08. Okay. So if I were to write the gain, let me take it to a next page maybe. So GM2 times the output resistance, okay, which is basically of the order of some GM R0 times another R0, right? So this is the current GM delta V times the cascode resistance, which is some GM R0 times some R0, right? So the gain is of the order of GM R0 square, okay? So this basically gives you, one order higher gain, right? So now we've seen it with the single-ended case. So now let's quickly make a differential equivalent. So it's going to be same. So this is a PMOS current source, PMOS cascode, and then you'll have the NMOS cascode and the final transistor where I'll apply the input, right? So I'll copy this to this side. Okay. So let's label the transistors like this. Okay, so this is going to be my V out. Right, and I mean all of these will be at some bias voltage, so I'll call it VB4, VB6 and VB8. So now can you quickly tell me what will be the output voltage, I mean incremental output? Okay, first of all, this is a completely symmetrical circuit. I apply plus delta V by 2 here, minus delta V by 2 here. What about this common source node? That will be 0. So what is the incremental current flowing here? Minus GM delta V by 2, right? So the current flowing up is basically the opposite of that. So you look at this guy, this is going to be plus. So this current flows into the output resistance. And what is the output resistance? You already know. GM4 R04 R02 in parallel with GM6 R06 R08. So the gain is basically this, I mean roughly it's GM R0 square by 2. So I'm just writing the order of magnitude, that's all. Let me just copy this. Okay, so now we have the differential thing. We'll convert it to a single-ended output. Okay, and for that, let me quickly remind how we did it for the 5 transistor case. So when we had the normal differential amplifier, we had a PMOS current source here, and we directly connected it to the NMOS, right? And if you think about it, the way we derived the final circuit was, we told we'll try to obtain this bias voltage for the PMOS transistor, and we wanted to be biased at such a voltage where the current flowing through the PMOS transistor is what? I0 by 2, right? And of course, initially we started with some separate branch and merged it in the same network. So, and that's what resulted in this diode connection, right? And again, if you think about how this came about also, let's say we connect it to some bias voltage VB. The PMOS is carrying some current IX, okay? But we want this current Ix to be equal to I0 by 2. I mean, ideally you assume that, let's say you calculate some bias voltage and you apply it here, thinking that the current flowing through the PMOS transistor is I0 by 2. But of course, obviously that might not be the case. There will be some current. So let us say Ix is greater than I0 by 2. What will happen to this voltage? I am pushing in more current into this node than what I am pulling out, and always there will be some capacitor associated with each of the nodes. If more current is pushed into a node, what happens to that node voltage? That will keep increasing, right? So this will increase, and in this case I should increase Ix or decrease Ix? I should decrease Ix. And Ix is the current flowing through the PMOS transistor. To reduce the current flowing through the PMOS transistor, what should I do to its gate voltage? So I should increase VB. So I see that this node is already increasing when we have the scenarios, and then we'll go and connect it. That's how we actually come with this diode connection. So now let's try to repeat the same here. Here we have a PMOS current source, but instead of connecting it directly to the NMOS side, we buffer the current and then connect it to the NMOS, right? Suppose it goes here. Okay, so we'll do the same thing. We want to generate the bias voltage for this PMOS so that the current flowing here is equal to I0 by 2, right? But we know that this, if you take the output here itself, it is not a great current source. So we'll take the current after the buffering. Okay. So now we'll compare this current, say some Iy with I0 by 2. So the same set of arguments hold good. So how can I generate this voltage now? I'll connect it to this node, right? Same thing. If Iy is greater than I0 by 2, this voltage will increase. And if Iy is greater than I0 by 2, I have to reduce Iy, which means I'll have to go and increase this gate voltage. And you already see that here this voltage is increasing when you have this current mismatch, so I'll directly go and make this connection. Fine? So that's what I'm going to do here. So this VB8 I'll generate directly by taking it and connecting it like this. Okay. Fine. Okay, so this might look very big, but if you think about it, it's pretty simple. This is basically our PMOS current source, right? The second stack we have here is the PMOS cascode. this was the NMOS cascode, and this is basically the final differential pair. Great. So now we have got this new circuit. Let's again try to repeat whatever we did for the 5 pack or the 5 transistor OTA. Forgot to make the connection. Okay, so first let's quickly find the DC operating points. So if this current is I0 by 2, what will be the DC currents in the transistors M1 and M2? I mean, I'm asking I1 and I2. So this is case, this is or this. It will be equal. Okay, I mean, we can argue the same way we did for the other thing, right? So if for these two currents to be equal, the drain to source drain voltages must also be equal. So which means these voltages must be equal, and if you assume they are not equal, you'll end up with some contradiction saying PMOS current is not equal to NMOS current. So again the same logic, I1 is I2, I0 by 2. So similarly, if I call the drain voltage here to be VD3 and the drain voltage here to be VD4, these two voltages will also be equal. Okay, and what is this drain voltage VD3 equal to?
VDD minus.
It's basically VDD minus this gate to source drop, right? Because this gate is what is connected here. Okay, so this is VDD minus source to gate voltage of the transistor. Which transistor? M7 at the current I0 by 2. Okay, so next let's look at the incremental gain. Again, this is an asymmetrical circuit, so we'll try to compute the short circuit GM and R out. Okay, so let's start with GM. To find the short circuit GM, what should I do to the output? Short circuit, because that's why it's called short circuit GM. Okay, and I'm interested in finding what is the current I out. Okay, and let's say I apply voltages V1 and V2. Okay, so now again let's not repeat everything. We'll try to use whatever results we obtained from our earlier analysis. So this drain is now short. Okay, and what is the impedance looking here? Okay, so let's say I apply a test voltage Vt. It is applied to the gate of M7 also. So what is the incremental current flowing here then? GM of which transistor? M7. That's fine. So this is going to be GM7 times Vt. Okay. Of course, we'll have R0 also. Finally, that will all get neglected, right? I mean, this current will flow here. I mean, you'll have a current due to GM. You'll also have a current due to R0, but finally the R0 will be so high that will not come into picture. So what is the impedance now? 1 by GM7. It should not be of surprise because basically this is supposed to be ideally behaving like a current buffer, right? You guys are okay that if I make this connection, it is 1 by GM, right? So here what I have done, instead of taking this current directly, I put a current buffer. I don't know what is the symbol for current buffer, but let's say this is the current buffer. So whatever current goes here comes here ideally, right? There is no difference here. Okay. So let me, how do I get rid of this? Yeah. So this impedance looking here is 1 by GM7, right? And I mean, so basically this is also at a very low impedance, right? Both of these drains are at low impedance. Okay. So approximately the bottom half looks like is symmetric, right? It's approximately symmetric. Okay. So then can you tell me what will this voltage be at? It will be average of the two. We calculated for the other case, this will be average of V1 plus V2 by 2, right? Because I mean you can repeat the same thing. You look at what is the impedance here, it will be 1 by GM, and then you have M1 here terminated by 1 by GM. Find what is this voltage and then do blah blah. Okay. So if this voltage is V1 plus V2 by 2, what will be the current here? Let me mark with some white color. What is the incremental current?
GM1 and 2.
So we call it I1. I1 is GM times
V1 minus V2 by 2.
V2 by 2. So the same current I1 will have to flow here, right? Now of course this current I1 also flows to the entire left branch, and the PMOS is basically a current mirror. So whatever current flows through the PMOS, that will also come here. So this is I1, this is I1. So what is I out? 2 times I1. So what is GM?
GM.
I mean, okay, this is GM. Okay, GM1. Again, this should not be of surprise because we started with this without cascode. There, the main transistor that was contributing to GM was this M1 and M2, right? We just changed the output impedance, that's all. So GM is not changed. Great. So if that is clear, let's move on to find the output impedance. Okay. So now let's find R out. So to find the output resistance, I will have to apply some test voltage at the output. I'll call VT. I'll try to find what current it supplies, and I'll short all the other inputs. Okay, great. And now this current again has two contributions, one up and down. Okay, so I'll write here, maybe save some space. So the total current is sum of I up plus I down. So let's first find what is I down quickly, because that is relatively easier. So if you look at the downside, you have M4 and then you have M2 and then whatever impedance is here. And what is this impedance?
1 by GM.
It is 1 by GM if this drain is at a low impedance. What is the impedance at this drain?
1 by GM3.
That is 1 by GM3 again if this drain is at a lower impedance. So what is this impedance then?
1 by.
That is 1 by GM7. That is for sure because that is diode connected. Okay, so this is 1 by GM7. So this is at a low impedance. So I can safely say this is 1 by GM3. Okay. So at M2 I have terminated with a resistor 1 by GM1. This is what we have looking down. Right, I'll call the impedance looking down as R down. So if you think about it, what we have is basically a triple cascode, right? So this portion here, this is the normal cascode, right? This is what we had for the earlier op-amp also. So if this as an equivalent resistance of some R prime, what is this R prime? That is looking here. So I mean, you write the complete thing of the impedance 1 by GM1 plus R02 plus GM2 R02 by, again GM1 is equal to GM2, so this is 2 times R02. This was same thing as we did it for the last op amp also, no change. Okay, so now you see that M4 is terminated by this 2 R02. So right, this is basically the R prime we calculated. So this is now again another cascode. So what is the looking impedance R down? Same for a cascode 2 R02 R04 plus 2 times GM4 R04 R02. And for all practical reasons, this is basically the last term only. Okay. So let me see if I can squeeze in something here. Okay, great. Okay. So which means now what is the current I down? The Vt by the looking impedance R down. So that's basically 2 times GM4 R04 R02. Okay. So now we know this is the down current flows. So this current again will have to flow up, right? So this is I down. I down will flow to the PMOS side also. It will get mirrored onto the this side. So basically you will have a contribution. I up will also have a contribution from I down. Okay. Plus you will also have a current flowing through the resistance connected at the drain and source. Okay. I mean this is the same thing as we saw. The current I up here will be due to the gate to source voltage and the drain to source voltage. Now if you think about it, this current I down is flowing, generating a gate voltage here, and the contribution due to the gate voltage we have added. The only thing pending is the contribution due to the drain voltage, and the drain voltage is basically V test, right? So whatever impedance the drain sees, that's what it is. And what is the impedance the drain sees? Looking up, what is the impedance? If there is no, I mean, assuming that gates are grounded, right? Because we have taken the contribution due to the gate, so we can ignore it for now. What is that? Not 8. Okay, is that fine? This is very similar to what we did for the earlier op amp also. Okay. So if it's not clear, please let me know. I'll explain it again. Okay. Great. So now we can write what is I test IT. What is IT? Right. Right. Okay. See, in the actual amplifier, the gates are not, all the gates are not incrementally grounded, right? Only this gate is incrementally grounded, that's all. And these two. We have the diode connection here that is still active, okay? And this is converting the voltage to the current, and the output resistance you have is this. Is that fine, or does it answer your question? We took the what?
We already took an amount of current going up through the transistor.
Okay, okay.
So I think I thought that the other part of the resistance will come as a series combination of the two R nowadays.
It won't be series, it will be parallel. Okay, see, like I mentioned, if you want to look, if you want to write the expression for I up, right? I up is the current flowing through this M6 M8 branch, okay, and the current flowing through the transistors, let me write it again. I up is flowing through M6 and M8, right? So this will be both due to VGS of M6 and VDS. Okay, now if you see the contribution we have from I down, this is the down current, this is clear. This down current is flow. Okay, let me redraw it and then explain it again, that might make it clear. Just give me a second. Yeah. So we know that the current, this is I down, everyone is fine with that. This I down flows here, that is fine. So if this current is I down, what will be this voltage? I'll call not Vx, maybe some Va. What will be Va? I down times the impedance it sees at that node. What is that impedance? 1 by GM7. So this is GM7. Okay. So this gate voltage is at Va. Okay. So now I up will have contribution both due to gate to source and drain to source. So what is a contribution from gate to source? That is basically GM of this transistor times the gate to source voltage we have. That is basically GM8 times Va, which is I down by GM7. Both sides are identical, so this is basically I down. Okay, so this takes care of the contribution due to gate to source. Now only drain to source is remaining. Okay, and I mean what I am saying is, since we have taken the contribution from gate to source, we can basically assume that for now this, I mean, it's not there, only this is there, that's all. And now you looking up, you see only this cascode here, and we know the impedance. Okay, is that fine? Okay, so let's quickly finish the calculation then. So this is the case. So what is I test then? This is I down, this is I up. Okay, I test is basically 2 times I down plus Vt by R06, right? So can you tell me what is R out then? GM4? Parallel with the other side, GM6. Okay, I mean again if you think about it, it just comes as the parallel, I mean the cascode impedance down, cascode impedance up, but that's not actually how it happens in this current mirror configuration, right? That's why I'm again going through this. If you didn't have this current mirror, it is straightforward, right? In the earlier case, I don't know where it is. In this case, there is no confusion. So this is completely symmetric. I can just consider 1/2. So looking up only is the cascode, looking down only is the cascode, because all the gates are incrementally shorted. Okay, but the moment we make this current mirror connection, that is no longer the case. We have this gate to be at some voltage, it is not incrementally ground, and that's why you will have to do all this. But finally, if you even after you do all this, this is what you get. Fortunately or unfortunately, that is the case. Okay. And again, now if you see that we have already 8 transistors here, and if you include the bottom one, you will have 9 transistors. So if you try to solve it by drawing the small signal equivalent and finding it, it becomes almost impossible. So that's why you should try to develop this sort of qualitative understanding and make some reasonable approximation to simplify things. That's why I'm doing it like this, right? Because if I start to draw small signal equivalent for everything, and that's it, I'll take 1 week for this to get go. Okay, so let me probably copy paste this again. So for this transistor, now we have calculated GM. What is GM? GM of these guys, right? GM1, and R out we saw was the parallel combination of GM4 R04 R02 in parallel with R08. So the gain is basically the product of these two. So I mean this in the so the gain is basically here some GM or not square of the order. Whereas when you didn't make this current mirror connection, it was half. Okay, that's all. Okay, so so for the we finished calculating the gain. So what else we did for the old op-amp? For the 5 transistor op-amp, first we found the operating point. We did that here. We found the incremental gain, that is also done. And what did we do in the last class? The common mode range and slew rate, right? So we'll just do the slew rate because that's simpler to do. So again, let's do slew rate. Okay. So for slew rate, again we'll consider that the op-amp is in feedback like this, and we apply a delta V u of t. Fine. And slew rate is basically the maximum rate at which the output can increase or reduce, and that maximum change happens at t equal to 0 plus, and at t equal to 0 plus the feedback is essentially not active. So it's as though we are applying this differential voltage directly. So I'll assume that between these two we apply a delta V. So now tell me what happens if delta V is very, very large, beyond some voltage. What will happen? I0 will flow to M1. So M2 can be considered to be out. And of course at the output I have a capacitor. I forgot to add that here. Okay. So I0 basically flows like this. The same I0 is going to be mirrored here. Okay, and that's going to flow through the capacitor CL. So what is slew rate? Same thing, I0 by CL. So similarly in the negative side you can again find out the slew rate is going to be same. That is, if you apply a large negative delta V, the other transistor M1 is now going to be off, and you can argue the same way. Great. So let's just quickly start with this common mode range and then continue. Okay. So now let's say we are trying to find the common mode range. I'll replace the current source by a transistor. Okay, so this is now VI. We are applying the same DC here. So what is the minimum voltage we can apply at the input? Sorry? Fine. I mean, we need to have a gate to source voltage across M1 so that it carries a current of I0 by 2. On top of it, we have to maintain this transistor M0 in saturation. So we need to have a minimum drain to source voltage, and that minimum drain to source voltage is basically VGS minus VTH, which in short we'll call it as the overdrive voltage. So I'll just zero. Okay, this is at the minimum side. Now if I keep increasing VI, what will happen? This transistor will go to triode, M1 and M2 will go into triode, right? So now maximum VI can go is what? If I call this as VB4, it can go VD4 plus VTH, right? right? And what is VD4? I mean, by the way, what fixes this drain voltage VD4 in the circuit? Huh? How is Vout fixing this drain voltage?
I not by 2 is
I naught by 2 is flowing, but that need not fix. I mean, ideally, if it has zero VDS dependency. Huh? How is M3 fixing it? Exactly. See, these two guys will have to carry the current I naught by 2, and I know their gate is at voltage VB4. Okay, so if the gate voltage is at VB4 and these transistors require particular gate to source voltage, what is VD4 then? I mean, probably I should not have called VD4, but anyways, yeah, what is it? VB4 minus. Okay, I think my terminology is slightly messed up. I will probably call it VD2, so that this drain of the transistor M2, right? After all, is that fine? I mean, this voltage, what I'm saying is basically the gate voltage minus the gate to source voltage of M4, so that it carries the current I naught by 2. Okay. So yeah, so which means what is the maximum of VI? This is VD4 plus VTH. Sorry, VD2 plus VTH. So VI max is okay. So let's stop here and we'll continue.